Welcome to EPG Pathshala. Dear students, today we are going to discuss on hydrogen as a fuel for future and fuel cells. As we all aware that fossil fuel combustion creates negative environmental impacts, especially related with their greenhouse gas emission. Hydrogen is universally accepted as a best preferred alternate to this fossil fuel because of its cleaner nature with no greenhouse gas emissions, and also it has potential energy carrier. So in this module, we will be going to discuss on why this hydrogen is an efficient fuel for the future, what are the properties of hydrogen, what are the hydrogen production processes. We will also see what is fuel cell, what are the different types of fuel cell, what is the working principle of it, also the microbial fuel cell and its types. Hydrogen is the simplest and most abundant element in the universe. The richest source of hydrogen is the water. Fossil fuels like petroleum, natural gas, coal and biomass are used as major sources for hydrogen production. It is a renewable energy resource, environmentally safe and can directly utilized for different types of fuel cells. Nowadays, it is used in portable electronics, power plants and in specially designed IC, internal combustion engines. The hydrogen and oxygen are the main fuel and oxidant which is used in most of the fuel cells. Let's see what are the properties of hydrogen. In this table, you can compare the properties of hydrogen with natural gas, petrol and LPG. You can see the heating values of hydrogen is very higher than the other fossil fuel. The lower heating value of hydrogen is 121 megajoule per kilogram, while higher heating value is 141 megajoule per kilogram. Now, coming to hydrogen production processes. The commercial hydrogen production technologies are catalytic steam reforming of the natural gas, naphtha or other hydrocarbons, partial oxidation of hydrocarbons, gasification of coal, etc. Most of the hydrogen in nowadays are produced in this world by the process of steam reforming and the water gas shift reaction, or as a byproduct of petroleum refining and the chemical production. If you see the contribution of this production process, you can say that the hydrogen production from natural gas, heavy oils and naphtha, coal are 40%, 30% and 18% respectively, while the contribution of the water electrolysis is 4% and from biomass is only 1%. So we have seen the conventional technologies for hydrogen production are steam methane reforming, that is SMR, partial oxidation, autothermal reforming, methanol reforming, ammonia cracking, thermocatalytic cracking of methane and novel reformer technologies are available. While the methods such as biomass gasification or pyrolysis, thermochemical and electrochemical splitting of the water and the biological fermentation are under development. Now, we will see in detail the most commercial way of hydrogen production, that is by the steam methane reforming. This process consists of two steps, that is reformation of natural gas. So the first step of SMR process involves methane react with steam at a higher temperature of 750 to 800 degrees Celsius to produce syngas or synthesis gas. It's a mixture of hydrogen and carbon monoxide. In the second step, which is shift reaction, which is known as water shift reaction, water gas shift reaction, the carbon monoxide which is produced in the first reaction is reacted with steam over a catalyst to form hydrogen and carbon dioxide. This process occurs in two stages, which consists of high temperature shift at 350 degrees Celsius and a low temperature shift at 190 to 210 degrees Celsius. Now, the hydrogen which is produced by this SMR process includes very small quantities of carbon monoxide, carbon dioxide and hydrogen sulfide as impurities. So, depending upon the use, it may require further purification. And the primary steps for purification include the feedstock purification, which removes poisons, which including the sulfur and chloride, to increase the life of downstream steam reforming and other catalysts. And the second one is the product purification, that is, in a liquid absorption system, carbon dioxide is removed. The product gas undergoes a methanation step to remove residual traces of carbon dioxide. So, the product purification is done after the process, while the feedstock purification is done before the process. New SMR plants utilize a pressure swing absorption unit, instead producing a 99.99% pure product hydrogen. Next is the electrolysis of water into hydrogen and oxygen with the help of electricity occur. In partial oxidation of heavy hydrocarbons, the hydrocarbon fuel, which can be natural gas, heavy oil, solid biomass or coal. These reacts with limited supply of oxygen. But in this method, it produces carbon dioxide as primary byproduct. In gasification or partial oxidation of coal, it is used to produce syngas. The coal is ground to a fine powder and then mixed with water to create a 50 to 70% solid content suspension, which is suitable for pumping and production of hydrogen. In this process, the maximum limit for the ash content of coal for the gasification in gasifier is 40%. In integrated gasification combined cycle for this Indian coal are under development, which improve its efficiency. Now, we will see in detail the hydrogen production from biomass. Biomass absorbs as much carbon dioxide from the atmosphere during its growth and is released during the conversion to hydrogen. It would be possible to sequester this carbon dioxide from the pressure swing absorption unit, which is resulting in a hydrogen process with a net negative carbon dioxide emission. It can be produced, or the feedstock can be used like energy crops, which includes herbaceous, woody and industrial, agricultural, aquatic crops, which are mainly related with the energy purpose. Agriculture residue and waste, which include the crop residue and the animal waste. Forestry waste and the residues, which include the mill wood waste, logging residues, tree and shrub residues. Industrial waste also used for hydrogen production. Municipal solid waste and even sewage sludge can be used for the hydrogen production. Let us see what are the different routes of hydrogen production from biomass. You can see in this flow chart, the biomass can be converted to hydrogen by means of thermochemical and biochemical ways. Under thermochemical conversion routes, they include pyrolysis and gasification, while in the biological conversion routes are biofertilizers, can be direct or indirect, dark and photo fermentation. Now, what are the thermochemical hydrogen production process? There are 4 thermochemical processes which are generally used for the energy production from biomass: combustion, direct liquefaction, pyrolysis and gasification. Among all these, pyrolysis and gasification are commonly used for hydrogen production. Hydrogen production from the biomass pyrolysis. The biomass pyrolysis occurs at a temperature of 650 to 800 Kelvin at 0.1 to 0.5 megapascal in the absence of air. The biomass is converted to liquid oils, solid charcoal and gaseous compounds by the pyrolysis process. Depending on the used technique, the products are 35% charcoal, 35% liquid distillate and 30% fuel gases, which include carbon monoxide, methane and hydrogen. As the products are mainly charcoal in the slow process, it is not normally considered for the hydrogen production, and mainly we follow the fast pyrolysis in the hydrogen production, which is a high temperature process in which biomass feedstock is heated rapidly in the absence of air to form vapor and subsequently condensed to a dark brown mobile bioliquid. So, the major hydrogen production by the pyrolysis is directly through fast or flash pyrolysis under high temperature and sufficient volatile phase residence time. You can see in this equation, the biomass plus heat produces hydrogen plus carbon monoxide plus methane and other products. Methane and other hydrocarbon vapors which are produced and steam reformed for more hydrogen production. So, you can see in the second equation, methane plus water produces carbon monoxide plus hydrogen. And in order to increase the hydrogen production, water gas shift reaction is applied. And it is like CO plus, that is carbon monoxide plus water will give carbon dioxide plus hydrogen. In favor of gaseous products, especially in hydrogen production, high temperature, high heating rate and long volatile phase residence time are required. The fluidized bed reactor type exhibits higher heating rates and it appears to be the promising reactor type for the hydrogen production from biomass pyrolysis. Coming to the biomass gasification, it is a two-stage thermochemical reaction consists of oxidation and reduction processes which result in gas and charcoal were free from the bio oil or the liquid component. The gasification occurs at high temperature above 1000 Kelvin. The charcoal is finally reduced to hydrogen, carbon monoxide, carbon dioxide and methane. So, you can see in this equation biomass plus heat plus steam will give you hydrogen plus carbon monoxide plus carbon dioxide plus methane plus hydrocarbon plus char. Unlike pyrolysis, this gasification of solid biomass is carried out in the presence of oxygen. Besides gasification, it aims to produce gaseous products, while pyrolysis aims to produce bio oil and charcoal. The biomass having moisture content, which is less than 35%, are used for this gasification process. Let us see what are the biological hydrogen production, which includes the organisms in its production. They are biofertilizers and the fermentation process. Biofertilizers of water. In this hydrogen production, this is mainly by using the green algae and blue-green algae, which is cyanobacteria. These are used for splitting the water and hydrogen is produced in it. And this is based on the concept of biofertilizers of water with the formation of oxygen and hydrogen. It can be direct biofertilizers or indirect biofertilizers. In direct biofertilizers, hydrogen is directly produced from water and sunlight. The solar energy is directly converted to hydrogen through photosynthetic reaction with the help of iron hydrogenase enzyme. It is similar to that of the photosynthesis by the plants and the algae, green algae. In this, the reaction is like this, water plus light energy, it produces or the water is split into hydrogen and oxygen directly. We have seen the next type as the indirect biofertilizers. In this method, it involves the separation of hydrogen and oxygen evolution in two separate processes or two separate stages, which is coupled through the carbon dioxide fixation and the evolution. The cyanobacteria have the unique characteristics of using carbon dioxide in the air as a carbon source and solar energy as the energy source. So, some cyanobacteria which are capable of indirect biofertilizers in which cells use carbon dioxide for the fixation along with oxygen release and further use this carbon fixed for the hydrogen production. So, this process involves separation of hydrogen and oxygen in two different stages. You can see these reactions as water plus carbon dioxide in presence of light energy produces C6H12O6, which is a carbohydrate which is glucose and which is a carbon fixed one along with the oxygen. And in the next step, this C6H12O6 reacts with the water and light energy to produce 12 moles of hydrogen and 6 moles of carbon dioxide. Now, in biofertilizers, we have seen direct and indirect biofertilizers where the splitting of water occurs. And in the next process, that is the fermentation process, here it can be photofermentation or dark fermentation. In photofermentation, it is carried out by the photosynthetic bacteria. This bacteria produce hydrogen from organic substrates that are catalyzed by nitrogenase enzyme in nitrogen deficient conditions in the presence of light. So, the equation is like this, C6H12O6, that is the organic substrate, plus water plus light energy produces 12 moles of hydrogen and 6 moles of CO2. Here the light energy is very much essential, and that is why the delta G0, which is the free energy, is positive. In photofermentation, you have seen 1 mole of glucose produces 12 moles of hydrogen. In dark fermentation, it is a anaerobic process that produces hydrogen from organic substrates without light. In this fermentation, the organic substrates are butyric, lactic or acetic acids which can be used for the hydrogen production. The majority of microbial hydrogen production is driven by the anaerobic metabolism of pyruvate, which is formed during the catabolism of various organic substrates. The breakdown of pyruvate is catalyzed by the enzyme systems like pyruvate formate lyase, that is PFL, and P4, that is pyruvate ferridoxin oxidoreductase. In dark fermentation, the reaction is like this. Glucose plus water produces 4 moles of hydrogen and 2 moles of carbon dioxide along with the acetic acid. So, you can see C6H12O6 plus 2H2O gives 4H2 plus 2CO2 plus 2CH3COOH along with the negative value for the free energy. Now, the hybrid reactor system, it is an integration of dark and photofermentation to produce the hydrogen continuously. Due to the requirement of external energy supply in the form of light, we have seen in the photofermentation the delta G was positive, while in dark it is negative. So, the complete conversion of glucose to hydrogen and carbon dioxide is not feasible if we follow one type of fermentation. In photofermentation, we have seen C6H12O6 plus 6H2O has given 12H2 plus 6CO2. And in the dark fermentation, where the external energy is not used, oxidation of glucose by the fermentative bacteria results in other byproducts, which is with the 4 moles of hydrogen, that is C6H12O6 plus 2H2O give 4H2 plus 2CO2 plus 2CH3COOH, but here no energy is used up. The acetate produced in this dark fermentation can be oxidized by photosynthetic bacteria to produce 4 moles of hydrogen, that is CH3COOH, that is acetic acid plus 2H2O plus light energy produces 4H2 plus 2CO2. Thus, integrating the dark and photofermentation, that means first dark fermentation followed by photofermentation, can produce a total of 8 moles of hydrogen if you compare that with the photofermentation of 12 moles of hydrogen, but here the energy required for the fermentation is less. Now, coming to the fuel cell. What is a fuel cell? It is an electrochemical energy conversion device that converts hydrogen and oxygen into water with electricity production, and the current that produced in a fuel cell is DC current, that is direct current. Hydrogen based fuel cells are most common type of fuel cells. Now, what is the principle behind this fuel cell operation? The fuel cell consists of an anode and a cathode, which is separated by a ion conducting electrolyte. At the anode, hydrogen and its electrons are separated so that hydrogen ions, that is a proton, pass through the electrolyte, while electron pass through an external electrical circuit as DC current that can power useful devices. So, the anodic reaction is like this. 2H2 produces 4H plus plus 4E minus, that is 4 protons and 4 electrons from 2H2 hydrogen molecule. Fuel cells generate electricity from a simple electrochemical reaction in which an oxidizer, typically oxygen from the air, and a fuel, typically that hydrogen is used, and they combine to form a product, that is water. This is the principle behind the typical fuel cell. The oxygen continuously passes over the cathode and hydrogen passes over the anode to generate electricity, and the byproducts are heat and water. Now, the hydrogen ion that pass through electrolyte from the anode reacts with oxygen and electrons from the external circuit to form water at the cathode. So, the cathodic reaction is like this. Oxygen plus 4H plus plus 4E minus give 2H2O. So, the oxygen is supplied from outside and 4H plus, that proton was from the circuit, and E electron is passed through the membrane. And the overall cell reaction is 2H2 plus O2 give 2H2O. So, the byproduct here is H2O, that is water, while the fuel is H2 and oxidant is oxygen from the air. The power output can be increased by combining the individual fuel cell to fuel cell stack. The power generated in the fuel stack depends on number of fuel cells in it and the surface area of each cell for voltage and current production respectively. That is, power in watt is equal to voltage in volt multiplied by current in ampere. Now, we will see what are the types of fuel cells. There are different types of fuel cells based on their operative type and type of electrolyte they use. The different types are PEM, that is polymer electrolyte membrane fuel cell, which is a low temperature fuel cell being developed for transportation and other portable application. Another type is PAFC, that is phosphoric acid fuel cell, and it is mainly used for the stationary applications. Other one is the molten carbonate fuel cell, the other one solid oxide fuel cell and alkaline fuel cell. This molten carbonate fuel cell and solid oxide fuel cell are high temperature fuel cells that are also suitable for stationary applications and are more efficient than PAFCs. Now, in this table you can see different types of fuel cells like PEM, SOFC, MCFC, PAFC and AFCs. You can see what are the fuel used in it. You can see the main fuel is hydrogen and the efficiency of those fuel cells are around 40 to 60%, and it has various operating temperatures. Some are having the low temperature operation while some are having the high temperature operation. Now, what are the benefits of fuel cells? It has direct energy conversion. Most fuel cell attributes on direct electrochemical power generation, that is without any combustion. In conventional power plant, more than 30% efficiency take place by the combustion process. Another benefit is high electricity generation potential. The high efficiency arises from the electrochemical nature of energy conversion, which is not limited by the Carnot cycle, unlike in the gas turbines and IC engines. The efficiency of fuel cell for generating electricity is around 40 to 60% and can reach even 85 to 90% in a combined heat and power mode. That means if the heat generated from the fuel cell is also used for the electricity production, we can increase the efficiency. It creates less pollution. The only emission from the fuel cell is water. When hydrogen is fed into the fuel cell, the byproduct is the water. Scalability is another benefit. The same high efficiency can be achieved by scaling up the fuel cells. A fuel cell does not have any movable parts for the generation of electricity, so the noise production by the fuel cell is not possible. Fuel cell technology can capture and store carbon dioxide. Unlike conventional electrochemical batteries, fuel cells consume reactant from an external source and it must be replenished as long as the reactant is available. The power can be generated. No restrictions on the fuel cell capacity. The benefits of hydrogen as fuel also include the use of hydrogen directly in the IC engines, mixing with diesel and CNG, and also in fuel cells to directly produce electricity. Hydrogen can substitute petrol and diesel and therefore reduce our dependence on the fossil fuel imports. Nowadays, it is also used as a fuel in spacecrafts. Now, it has limitations also. The main issues related with hydrogen is the storage. The present cost of onboard hydrogen storage system is very high as compared to petroleum fuels. The weight and volume of hydrogen storage system are also high, which results in inadequate vehicle range compared to conventional petroleum fuel vehicles. Energy efficiency is a major challenge for all the hydrogen storage approaches, including the reversible solid state materials. compression and liquefaction techniques. The life of hydrogen storage system needs to be improved, especially for the solid state storage methods. Refueling time for onboard storage is also linked with the performance characteristics of the fueling station and its compatibility with the onboard storage system. As hydrogen is a colorless and odorless gas, suitable methods will have to be developed to detect possible leakages in pipelines and in stacks of tanks, cylinders at the refueling stations. Currently, used hybrids have low weight percentage of hydrogen storage capacity, which makes them bulky. So, these are the limitations which related with as a fuel. Now, the applications of fuel cell we have already seen, but we can summarize it as stationary power generation. It is used in the stationary power generation. The main desired characteristics are high efficiency and long lifetime. Their power generation capacity ranges from a few hundred kilowatt to several megawatt. More than 2,500 fuel cell systems have been installed all over the world, especially in hospitals, nursing homes, hotels, office buildings, schools, utility power plants, either connected to electric grid to provide supplemental power or as backup assurance for critical areas, or installed as a grid independent generator for on-site service in areas that are inaccessible by the power lines. Another use or application is in the transportation sector. Currently, most major automakers are working to prepare fuel cells for cars due to their high efficiency and low emission. Fuel cells are powering buses, boats, trains, planes, scooters, and even bicycles. The successful introduction of hybrid electric and combustion engine cars, or more recently the plug-in electric cars, are examples of these types. Third application is the portable application. The portable fuel cells can also be used as a reliable source of emergency backup power. Miniature fuel cells for cellular phones, laptop computers, and portable electronics are also on their way to market. The hydrogen-based fuel cell is used in auxiliary power units for, that is APUs for the vehicles, electricity storage by regenerative fuel cells, space applications, and military applications. Now, what are the fuel cell R&D, research and development in India? In India, the development of fuel cell is primarily supported by Ministry of New and Renewable Energy Sources. Bharat Heavy Electricals Limited is involved in the development of PAFCs and plans to develop a 50 kilowatt stack. The Energy and Resource Institute has in the past demonstrated the use of biogas for generating electricity from a 2.5 kilowatt PAFC stack imported from Energy Research Corporation USA. In addition, MNRE has funded the import of a 200 kilowatt PAFC system made by the ONSI to evaluate its operation. SPIC Science Foundation is working on PEM, polyelectrolyte membrane fuel cells. SPIC Science Foundation is working on PEM fuel cells and has developed stacks. They have also demonstrated a fuel cell battery hybrid vehicle using a 10 kilowatt PEM power plant. Work on an MCFC stack is also underway at TERI and Central Electrochemical Research Institute. Work on an MCFC stack is underway at TERI and Central Electrochemical Research Institute. Work on developing direct methanol fuel cell is also underway at Indian Institute of Science. In addition, research on solid oxide fuel cell is being done at IISc and Central Glass and Ceramic Research Institute. Research and development on metal hybrid storage is ongoing at Banaras Hindu University. Now, we will see microbial fuel cell. The fuel cell that generates electricity with the help of microbe is known as microbial fuel cell or MFC. The biochemical energy produced during metabolism of organic substrates is converted to electric energy. MFC consists of anode and cathode separated by proton exchange membrane, and both electrodes are connected by an external circuit. At the anodic chamber, the oxidation of organic substrate in the oxygen by the respiratory bacteria generate electrons and protons which are carried to cathode through circuit and the membrane respectively. the principle of the microbial fuel cell. The anodic and cathodic reaction of a microbial fuel cell working with acetate along with external supply of around 100 milliwatt is as follows. In anode, acetic acid is there, and anode acetic acid plus water give 2 CO2 plus 8 H plus and 8 electron. And this at the cathode 8 H plus 8 electron produces H2. The types of microbial fuel cells. There are two types of microbial fuel cell, mediator based microbial fuel cell and mediator less microbial fuel cell. In mediator based microbial fuel cell, the microbes produce soluble redox compound such as quinones and flavins or exogenous mediator such as dye, that is neutral dye, methyl blue, anthraquinone 2,6-disulfonate or metalloorganics to carry electron between respiratory enzyme and anode surface. Examples for this mediator based hydrogen production are Klebsiella pneumoniae, Erwinia dissolvent, Proteus mirabilis, which are involved in the mediator based MFCs. The second type is the mediator less MFCs, in which the direct electron transfer to anode by bacteria require a physical contact with the electrode for the current generation. The electrochemically active proteins such as the cytochromes and other outer membrane, electrochemically active proteins such as the cytochromes on the outer membrane transfer electrons directly to anode. And the examples of these mediator less hydrogen production by the microbes like Aeromonas hydrophila, Geobacter metallireducens, Geobacter sulfurreducens, Rhodophyrex ferrireducens, Shivanella putrefaciens, etc. So far we have seen the high efficiency and the lack of emission make hydrogen as an alternate fuel and as a fuel in fuel cells. The emerging hydrogen production technologies may provide low cost clean hydrogen in the future for the automobiles and power generation. And in this module, we have seen why the hydrogen is used as an efficient fuel for the future, what are the properties, mainly the high calorific value in comparison to the other fossil fuels like petrol, natural gas, etc. We have seen different hydrogen production processes like SMR, that is steam methane reforming, electrolysis of water, and also the biomass based hydrogen production. It includes the thermochemical and biochemical processes, which includes the thermochemical and biochemical processes. Like in thermochemical process, we have learned about the pyrolysis and gasification. In biochemical process, we have seen the biofertilizers, which is direct or indirect, and the fermentation, which is dark or the photofermentation. And we have seen how much hydrogen is produced from the different types of fermentation. We have also seen the fuel cells. What is a fuel cell? It's an electrochemical energy device which converts the hydrogen and oxygen into water with electricity production. We have seen different types of fuel cells like polymer electrolyte membrane fuel cell, molten carbonate fuel cell, solid oxide fuel cell, alkaline fuel cell, etc. And we have also seen the working principle of a fuel cell. And we have seen microbial fuel cell is a fuel cell that generates electricity with the help of microbes. And there are two types of microbial fuel cell, which are mediator based and mediator less microbial fuel cell. Thank you.